Hi everyone. Today, actually, I'm going to do a small video to explain actually why we have to stay at home this time. So this is based on this COVID-19 problem. It's a kind of a mathematical approach based on differential equation, and we'll explain the situation. Suppose this is our population, this is our country or our village, and this part is called susceptibles. That means people who have not got this disease. This is called infected area. This is they have got the disease, and this is called R. That means people who got the disease, but now they don't have the disease. Now they have recovered, or maybe dead. Okay, so then we have three things: S, I, and R. So some portion from S to go to I, so then I to R. Some people are getting the disease, some people are getting recovered. And from S to I, the ratio is simple R. So then based on this one, we are going to make a small constructed differential equation. So differential equation is ds over dt, it's equal to minus R I times S. So basically this I denote infected areas and S denote susceptibles, and S to I, the R denote the rate, how many, so what is the portion of the S is moving to I section. So this is negative because S is people who are surviving so far, but then at given any time they can move to I. So that means actually it's getting decreased, this S, day by day. Some people are getting the disease, so that means the people who don't have this disease, then this number is going down. So that's why ds over dt become a negative value. So this is your first differential equation. And the second differential equation is di over dt. You can differentiate with respect to time. Then you get we are going to construct it RIS. So this is the people who are getting the disease infected part minus A times I. That means people who are getting the recovery part. So this is the recovery section. This is the infected section. Infection minus recovery is used like removing all the recovered people from the infected people. So you get the 100% only infected people. So that part is also going up. That's why we can say di over dt. This is your second one. Right, now we can divide the first one, so the second one by the first one, di over ds. We can come up with di over ds. So di part is ris minus ai, and then divide by minus ris. Now we can simplify this. You get minus 1 over plus a over rs. And then we can see this a over r, this segment. According to the definition, we call them q. Q is r over a. So then we can replace that part by r over a. The I by ds is equal to minus 1 plus 1 over qs, where q is r over a. Now we have a differential equation, very clear. Di over ds, it's equal to minus 1 plus a over r s. Actually, I have to tell you about this. Sorry, this is qs. This one is now we proved that this is 1 over qs. Actually, I have to tell you something about this q. This q, it's kind of a fraction of population which come into the contact. I mean, so this population, actually q, they don't have the disease, but they are coming into contact with the patients. So that is the q part. So then maybe we want to come up with the maximum infected people. We are going to get I max. Our target is to find I max. This is our target. Okay. So, right. For that one, normally we have to make it equal to 0. So then you get minus 1 plus 1 over qs. The rate of change is 0. Then you can come up with s equal 1 over q. This is your first one. This is a special kind of S. And at the same time, we can take this differential equation di over ds. You can cross multiply, then you get di equal minus 1 plus 1 over qs into ds. Now this you can integrate both the side. This would be I equal minus s plus 1 over q ln s plus c1. C1 is the constant. To find C1, we can use this initial condition. We assume that susceptibles, the initial susceptibles S equal S naught, and initial infected people I equal I naught, and initially we don't have any recovered people, 0. So when you plug those values here, you can understand, you can take this I plus S minus 1 over Q ln S equal to I naught plus S naught minus 1 over Q ln S naught, right? Then you can see this S value. We understood when S equal 1 over Q, you get the maximum I. So now you have a chance to tackle this I max. That would be, you can write down somewhere here. I max value is equal to I naught plus S naught minus 1 over Q 1 plus ln QS naught, right? Okay, actually this part is our population. This is the total population. This part I can denote as function, say f of q. This is another function, f of q. Now to understand this function, I want to plot it. This is q and this is f of q. In this function, when you check the different key values, it goes up and it's going down like this. So this is very sharp increase. When it comes to S naught level at a particular Q value, that's the maximum value. So this is not the maximum value, but this help you to understand the maximum I value. But what I want you to consider is this portion FQ function segment, function part. We have to, if you want to keep this maximum value as it is, I mean, like if you want to keep this one as a very big value, we can let it be, it's okay. But if you really want to reduce this one, I mean, this denote our country maximum infected number. Maybe this is not now, it is in future. So if you want to reduce this value, you have to reduce this part, you have to minimize this part. When you are minimizing this part, actually the whole thing must be minimized, but this part must be maximized. Then only we can minimize this part. When you are maximizing this, you can understand, since this is 1 over q, we have to minimize the q value. So q we have to minimize. Then only we can reduce our maximum infected patients. These are future number, but we have to minimize that one. So this maximum I value we are going to minimize. I mean, that means we don't want much people to get infected. We want to keep it like very low value. That's why this q must be very the small value. So this q denote contact ratio. That means the fraction of population which come to contact with this individual. That means the people who are getting, let's say when the government is releasing, sometime they are removing curfew, people are coming out. That is the q. So we have to reduce that q. Then only when you minimize this q, you can put this part down. So that means we will not have a lot of people, a lot of death. We will have very small number of maximum. So that's what actually we want. Our government wants everyone that. So please understand this. My request is please stay at home and we have to minimize this q value. Thank you very much.